Hello everyone, welcome back. Today we are going to deal with master theorem. We have been solving recursive or recurrence functions. We have already seen substitution method and recursive tree method. Topic of today's discussion will be master theorem. Okay, so let us begin. What is master theorem? It's again a way of solving recurrence functions, but there are some limitations. First of all, when you are going to start solving any recurrence function, it must be in a specific format. The format will be, I shall say, valid format for master theorem. The function shall be in the form of t of n is equal to a times a is a constant, t n power b, n by b, sorry, plus f of n. Alright, here a and b shall be greater than 1, but a can be equal to 1 also. A can be equal to 1, b must be greater than 1. Okay, so if a given recursive function is in this format, then I can apply master theorem to find out the value of function. Okay, now there are three cases which will tell me how to find out the value of this function. First case is if f of n is equal to big O of n raised to the power log a base b minus epsilon. If this holds good, then t of n is equal to theta of n log a base b. I'll be explaining all of this. Just hold on for a second. I'll write all the cases, then I'll go into explanation. Also note that here epsilon is greater than 0. Epsilon is greater than 0. Second case is if f of n is equal to omega of n power log a base b plus epsilon, then t of n is equal to theta of f of n. Same situation, epsilon is greater than 0. Third case states if f of n is equal to theta of n raised to the power log a base b into log n power k. Okay, ab will be given by this function. A can be equal to 1, b has to be greater than 1, and k value in this case has to be greater than or equal to 0. Okay, this is the condition. If this happens, then t of n is equal to theta of n log a base b times log n power k plus 1. That is the only difference. So now we got three cases of master theorem. I'll be explaining what is the essence of it. Okay, so we can see t of n depends on f of n, a and b. Okay, so these three things, a, b and function, will determine the complexity of t of n. So if f of n is having higher complexity, definitely t of n will have a complexity of order of f of n. If the other part, which is n raised to the power log a base b, is having higher complexity than f of n, then it will become the complexity of my recursive function. Okay, I'll explain it with an example. Say we have this example. T of n is equal to 8t n by 2 plus n square. Here I can see, if we compare with this function, it is in the format a t n by greater than 1 plus f of n. This happens to be in this format. So I'll check for each case. If first case is not applicable, I'll check for second. If both are not applicable, then only I'll check for third. Obviously, only one case will be valid. So here from the given equation, I can say a is 8, b is 2. This implies log a base b is equal to log 8 is equal to 3. F of n is equal to n square. N raised to the power log a base b turns out to be n raised to the power 3. Okay, so now you see, we can see which function is growing faster. Clearly this function is growing faster, so this will become the complexity of t of n. Okay, how will we match with the cases? Now see, I can write these two as f of n, which is equal to n square, is equal to big O of n log a base b minus epsilon, if epsilon is equal to 1. Okay, f of n is equal to n square is equal to big O of n cube, which is log a base b minus 1. So 1 becomes epsilon, and it is greater than 0, is equal to big O of n square. So this condition holds good. Holds good means case 1 satisfied. If case 1 gets satisfied, we can say T of n is theta of n power log a base b. N power log a base b is n cube, theta of n cube. Okay. So the meaning of this will be, what do we mean when I say minus of epsilon? Okay, this can be written as n power log a base b by n power epsilon. Right? This means I have my function which is given in the definition, and if I can divide that by some polynomial, n power epsilon is essentially some polynomial, and then I'm able to reach the level of f of n, then definitely this function is greater, because I have to divide by a polynomial to reach something. That means that thing is greater. Okay, how do we compare 5 and 2? If I divide 5 by 2.5, then I reach the level of 2. So there is a polynomial times factor. Okay, so the factor that is differentiating f of n and n power log a b is n power epsilon. If this factor exists, then obviously n power log a base b is having higher complexity than complexity of f of n. Therefore, in order to determine complexity of t of n, n power log a base b will contribute more. And while calculating complexities, we ignore the function which is contributing less. So we ignore f of n. Our answer will be t of n is theta of n power log a base b. That is demonstrated in this example. Let us take another example to demonstrate second case. The second case is t of n is equal to 2 times t of n by 2 plus n square. Okay. 1 second please. Okay, t of n is equal to 2 times t of n by 2 plus n square. So this is also satisfying. This format. A happens to be 2, b happens to be 2. This implies log of a base b will be 1. Log 2 power 1 is 2. This implies n power log a base b will be n power 1 is equal to 1. And f of n is given to be n square. Now I can write it in the format of case 2. How? That f of n is equal to omega of n power log a base b plus epsilon. If epsilon is equal to 1, we can see f of n is n square. N power log a base b is n. So I can write it as n power 1. If I add 1, then they are asymptotically as well as mathematically equal. Okay, so I am adding a polynomial factor. Okay, I need to multiply n power log a base b with a polynomial of n in order to reach the lower limit of f of n. That means f of n is larger, means growing faster, asymptotically larger than n power log a base b. This implies it will contribute more towards asymptotical complexity of t of n. Therefore, I can say this satisfies case 2. If case 2 is satisfied, I can say t of n is equal to theta of f of n, and theta of f of n is n square, so theta of n square. T of n is equal to theta of n square. Alright. So these two problems demonstrates first case and second case. Now from this you understood whichever function is having higher asymptotical complexity, that will determine the asymptotical complexity of t of n. But what if both of them are having equal complexity? That case is dealt with case 3. Okay, if f of n is having theta times this can be assumed as equal, because theta essentially means equal. O means upper bound, omega means lower bound. Theta can be set as equal because it will determine the range. Then t of n becomes, I will just increment the logarithmic factor of n. Where it was k, I increment it to k plus 1. Okay, and let us take another example to understand this. Example 3. In example 3, I have t of n is equal to 2t n by 2 plus n. It satisfies the format of master theorem. If a is equal to 2, b is equal to 2. This implies log a base b will be equal to 1. This implies n raised to the power log a base b is equal to n power 1. And f of n is also given to be n. Now you see, mathematically both of them are equal. But I can write f of n is equal to theta of, look at the given format, n power log a b, the value which I calculate, n power a times multiplied by log n power k. Okay, so here it is getting multiplied by 1. Okay, f of n is, this can be written as theta of n, right? I wrote that as it is. Now this can be written as theta of n power 1 times log n power 0. K can be greater than or equal to 0. Just note, k can be greater than or equal to 0. Here k happens to be 0. If this condition is satisfied, then case 3 of Master theorem will come into play, and we can say t of n is having a complexity, same function, okay, same function, and log n, and we will increment the power of this by 1. So 0 increment 1 will become 1 is equal to theta of n log n. Okay. Okay, now let us take example number 4. So I am given t of n is equal to 16t n by 4 plus n. And how will I approach it? I can see a is equal to 16, b is equal to 4. This implies n raised to the power log a base b is equal to n square. Okay, and f of n is given to be n. So in order to reach f of n, I need to divide n square by n. Okay, divide by n power 1. So this is having higher complexity, so I can directly say t of n is theta of n square. N square is n log ab. N log ab. Direct answer. Example 5, which is if t of n is equal to 32t n by 2 plus n power 6. So n power log a base b is equal to n power log 32 base 2 is equal to n power 5, and f of n is given to be n power 6. Clearly f of n is greater than n power 5. This implies t of n will have a complexity of same as that of f of n is equal to theta of n6. Example 6. Okay. Example 6 is t of n is equal to t of n by 2 plus n log n. So a is equal to 1, b is equal to 2, log a base b is equal to 0, n raised to the power log a base b is equal to 1, n power 0 is 1, and f of n is equal to n log n. Alright, so if this is the case, then what can I say? F of n is equal to, here f of n is equal to n log n times greater than n power log a base b, because this is 1. I have to multiply with n log n in order to reach this level. If I multiply 1 with n log n, I will reach this level. Here the point to be considered is, if I am having n power 1 getting multiplied, or n power 2, or n power 3, or n power 4, I will consider this as polynomial, not as a logarithmic function. Okay, because order of growth will be determined by n, not by log n, because n grows faster than log n. So if I multiply this with a polynomial n log n, then I'll be able to reach the complexity of f of n. So second case gets satisfied. Okay, second case gets satisfied because in this case we have f of n having higher complexity than n power log ab, and I need to multiply with a polynomial. That condition is satisfied. This implies t of n is equal to theta of n log n. Okay. Next question is example 7. Example 7 is given as t of n is equal to 2 times t of n by 2 plus n log n. Okay. So from standard format we can say a is equal to 2, b is equal to 2. This implies n raised to the power log a base b is equal to n power 1, and my given function f of n is equal to n log n. So you see clearly n power log ab is log n times lesser than f of n, but I'll have to multiply with a factor of log n, which is not a polynomial, does not belong to polynomial. Okay, this implies case 1 is directly failed. Okay, case 1 says n power log ab is greater, n power log ab is definitely not greater, so case 1 fails. Case 2 fails because we are not able to find any polynomial power. I need a polynomial here. You see, I need a polynomial. If I'm not able to find a polynomial which can be multiplied with n power log ab to reach the complexity of f of n, then case 2 will also fail. Now checking for case 3. Okay, case 3 says if f of n is equal to theta of n power log a base b times log n power k. Okay, we need to check if this condition holds or not. So in our case it is given as n times log n. This is exactly equal to n power log ab. Okay, and this value is 1. Alright, therefore I can say t of n is equal to theta of n log n. I'll increment the power by 1. Okay, for k is equal to 1, this condition holds good. We want this condition to satisfy. This condition is getting satisfied for k is equal to 1. If this is getting satisfied, then t of n is equal to theta of n log n, and power will be incremented by 1. Okay, next question. Okay, now we have understood how are we approaching. Let us just focus on n power log ab and f of n, so that I can demonstrate the things which you may occur while solving some problems. Say f of n is equal to n raised to the power log n this power 9, sorry, it's getting multiplied, n times log n power 9, if this is happening, and n power log a base b is given as 1. Okay, so this is my given question. 9 is in power n into log n power 9, n power log a b is equal to n power 1. Okay, so a is equal to b in this case. How are we going to approach it? From previous analysis we know we have to compare f of n and n raised to the power log a base b, whichever is greater that will contribute to t of n, but there are some limitations. Now in this case we can see f of n is equal to, I can write f of n is equal to theta of n power log a b times log n power k. Yes, this is equal to this, and k is equal to 9. This condition is getting satisfied. If this condition is getting satisfied, then I can say t of n is equal to theta of n power log a base b log n increment power by 1 is equal to theta of n power log a base b is given as n power 1 times log n raised to the power, here k is 9 and plus 1 is 10. T of n is equal to this. Okay, next question, example 9. Okay, in this one let us say f of n is equal to n and n power log a base b is equal to n log n square. Okay. So how will we approach this? We have to compare f of n and n log a base b. Clearly this function is greater, but it shall be polynomial time greater. Okay, so the polynomial which we will need to multiply, okay, will be n log, okay, it is not n square, it is n, both are equal. Okay, so the factor which makes it greater than this is log n whole square, which is non-polynomial. Okay, if this is not getting satisfied, then we can say that master theorem is not applicable. Okay, see, f of n is clearly less than in growth than n power a log b. Okay. So you see f of n is less than n power a log b, so case 1 shall be satisfied, but no, case 1 is not satisfied because it shall be polynomial time greater. It is not polynomial time greater, it is logarithmic times greater. So if it is logarithmic times, we cannot apply Master's theorem. Next example, if t of n is equal to 2 power n t n by 2 plus n square, then n power log a base b will be n power log 2 power n base 2 is equal to n power n, and f of n is equal to n square. So clearly n power log a b is greater in growth than f of n. That function is greater, but mind you that it shall be greater a constant polynomial times. Okay, if it was 3 or 4 or 5, then we could say that epsilon value is a constant, where epsilon shall be greater than 0 and must be a constant. K shall be a constant, a and b has to be constants. Okay. Here the value which is the factor which makes it greater is n minus 2. Okay, these many, like what I'm trying to say is I'm comparing n power 1 and n power 2. So this is n power 2 plus n minus 2 is n square. So the factor is n square. So this function on the left hand side is this much times greater than the function on right hand side. But this, it is a polynomial, but we can't find epsilon. Okay, because the power here is not constant power. It is a function of n in fact. Okay, it is n minus 2. So here also we cannot apply Master theorem. Next example, it's given that t of n is equal to t of under root n plus some constant c. Okay, so comparing it with the given format of Master theorem, we may think like Master theorem is not applicable here because Master theorem is defined on n. Okay, So we may think like it is not applicable. So there will be two approaches to solve if this question arrives in an exam in front of you. Then either you can go for substitution method, because if you have practiced enough, it is very easy, or you can think, you can imagine, and you can reduce it in this format. Okay, so there is a replacement, means substitution only, but we are trying to bring this function in the format of master theorem so that we can apply cases. Okay, so if this is my given function, I will say n is equal to 2 power k. Okay, say n is equal to 2 power k, I am assuming. Then t of 2 power k is equal to t of 2 power k by 2 plus a constant c. Also now we still do not have our function in terms of master theorem. Okay, so now let me again assume that t of 2 power k is some function s of k. Okay, whatever was the power, I'm keeping it as a variable of s. Okay, so this function will become s of k by 2 plus c. So t of 2 power k becomes t of 2 power k becomes s of k, which will be equal to s of k by 2 plus c, s of k. Okay, now s of k by 2 plus c, a is 1, b is 2, log a base b is equal to 0. This implies n power log a base b is equal to 1, and we have a constant here, so constant can be written as c dot n power 0. Okay, so my function is some constant times n power 0, and n power log a base b. So first and second case failed. Let us try to write f of n in the format of c. Okay, c can be f of, or shall I say, theta of c, right? Theta of c is theta of 1. Theta of 1 is equal to theta of 1 times log n power 0 is equal to theta of n power log a base b log n power 0. Okay, good. So here I wrote n, it is k. Okay, this is happens to be the case 3 of master theorem. So I can say that t of k, like my given function is s of k. S of k is having complexity theta of, this is 1 times log k power 1 log k. Okay, also note that I said s of k is equal to t of 2 power k. So t of 2 power k has the complexity this. Okay. 2 power k is n. 2 power k is in place. K is equal to log n. T power 2k is equal to t power n. So t power n is equal to theta of log of k is log of n. Okay, this will be the answer. That's it for this video. Next, we'll be dealing with application of master theorem, and applications include sorting techniques. Okay, before application in divide and conquer, I'll be trying to explain abstract algorithm, what is meaning of divide and conquer, and then we'll be dealing with some problems to find time complexity of a divide and conquer algorithm. Then some applications such as finding maximum minimum of number of an array. In the array, what will be the minimum time complexity? We will try to optimize the time taken to find the minimum and maximum element of that array. How to calculate power of an element using divide and conquer. Binary search. In binary search, I'll also be covering linear search. Okay, I'll be explaining linear search with it. Okay, merge sort. Selection procedure. The selection procedure uses merge sort. So after merge sort, we'll go for selection procedure. Quick sort. After quick sort, number of inversions, because number of inversions will use the method from quick sort. And last is Strasson's matrix multiplication. So see you in the next one. Till then, take care. All the best. Bye.